All right, so here we go. "25 questions. Hurry up." Only got 4 seconds. All right, good job. Looks like people got that. So there were a couple right answers there. And this came up when we did the crossover design with repeated measures. And to get, if you want to do like the AR1 structure applied just to within a period, then you could either, the only real difference between these is one has the day mentioned and the other one doesn't. But as long as the data are sorted, you could do it with the green approach. But looks like most people got that one. So now you understand the time. You can see the time ticking down. And most of the answers are not multiple select. There are some in here that are, but not everyone. All right, here we go. Question 2. And there's the leaderboard. All right, here we go. All right, most got it right. I think the thing that tips this one off is, well, at least simplifies the possible answers, is correlation. What do you know about correlation? 47 is not a correlation. So that's good. No one answered that one. And so if it's covariance, it could have been sigma squared B, and that maybe that's the thing that threw a few people off. But it's correlation. It's not 0 because you have the random intercept. If it was just the AR1, then it would be 0. But since we're adding the random intercept, then the asymptote is sigma B over the square root of the sum of those two other variances. So this relates to a homework question that we had. And let's see what the leaderboard looks like now. All right. Caitlin's doing pretty well so far. Would it help? Do you just want to read it yourself, or do you want me to read it? What's the easier way to do like we're doing? All right. Question 3. So the what model is used to conduct inference for random effects? It is a conditional. It's based on a conditional distribution, conditioning on the random effects. It's also a Bayesian model. So either one of those is correct. Leaderboard. Wow. Okay. All right. Next question. Nice job. Profiled likelihood. That's a good review question. There's so many different types of likelihoods that we talk about in this class. And so the profile likelihood is just like the regular maximum likelihood, but you're just re-expressing it in terms of a subset of parameters. And for a linear mixed model, we typically do that. We write the profile likelihood in terms of the covariance parameters. All right, leaderboard. Nice. Poisson and negative binomial, two common count distributions. There's the leaderboard. Jonathan has the highest answer streak of 5. So he's kind of charging to the front here. Nice. Good job. So we get that when we, in Proclimix, if you're using SAS, you add the random residual, right? And if you specify, like you could specify the AR1 structure, or you could just have the residual variance itself without the AR1. But either way, the residual variance is going to be, it's going to act like the dispersion parameter. And that's something we learned in one of the homeworks. Oh, some movement there. Multi-select. What's Matt's favorite meal? This is important. Let's see how well you know me.
Where is the full enchilada on this?
That's right. I forgot about that. So, you know, I guess tamales may not have, that's close to enchiladas, isn't it? I'm happy that you got the homemade pasta. That's good. You kind of know me. I'm a runner. I like carbs and stuff. So that's correct. I love tamales too, and pretty equally between those. If I had to pick one, it would probably would be pasta. But I like tamales enough to make that, you know, a co-favorite. So good. You didn't get the tamales, but you got the pasta. So I figured I'd add a couple. There's a couple more kind of fun ones in here. Oh, nice. Look at that. That changed things up there. Here we go. Population average. So the GE models, if you have subject heterogeneity, like if there's random intercept differences in the population, but you don't include that in the model, and for GE models you don't have the option to add random effects, and so that's why the beta parameters end up being what we call population average effects. And for other generalized linear mixed models, really, I guess you don't consider GE generalized linear mixed models, but for the generalized linear mixed models, if you add in the proper random effects, then you have subject-specific interpretations. But the GE have population average interpretation, so most people got that. All right. What's going on, Jonathan?
This light turns itself off based on motion. And so
Oh, okay. I thought you're swatting it like an animal flying around above you. All right, here we go. All right, nice. So the transform data so LMMs can be employed is a correct answer. When we approximate the true likelihood using quadrature, that's the other general approach to fitting a generalized linear mixed model. So both of those, the red and the gold, you can do through proc-limix, but the difference is in in the method that you select, whether you select method equals quad, which would be the gold one, where you're approximating the true likelihood, and method equals RSPL, RMPL. Those things are the linearization or the pseudo likelihood approach. And if you don't say anything, if you don't say method equals anything, and you leave that out, the default is RSPL. It's actually a pseudo likelihood approach. Chloe, nice job. Good. Yeah, I wasn't sure about, that's good. I wasn't sure if you would remember this one, but, and we'll actually see a data set today where, if you just apply the AR1 structure, that you'll see a correlation a certain amount. When you add in more stuff, it's going to account for some of the correlation. So the correlation for the AR1 is likely going to decrease. Right. A lot of movement up and down. So it should be interesting to see what happens here. So we're not quite halfway through. That was close. So the coefficient of predictor measured with error will likely be attenuated. It'll be moved towards 0. Could it increase? It's not likely. I think it's like if it's measured with error, we would expect it to be attenuated, move towards 0. So we can review the measurement error slides as well to get more detail on that. Right. Good job. So for marginal structural model, we estimate causal effects by applying weighting to individual records. And that's kind of just a very crude, short statement, but the other ones are not the approach we would use for marginal structural models. And you can review that more in detail as well. But one of the key things is we apply that weighting approach to treat it as if if subjects were randomly assigned treatments, a way to mimic that. Good. So it's true that, in the marginal model, which is probably the thing think about the first, that's the standard frequentist type of inference that we do. But we do Bayesian for the random effects. So it's both of them. Yeah, so that's that. Wow. 14. All the answers are in already, so I think you probably got this one. Nice, you all got it. Good job. So you do get more points if you answer quicker. I probably should have mentioned that earlier, but the quicker you can answer, the better. But obviously, you want to make sure you get it right as well. So here's a multi-select. Yeah, so it's the compound symmetric and AR1. So you can see how the AR1 is very efficient because it's a realistic covariance structure for repeated measures, but you only have 2 parameters, and that's not any more than the compound symmetric, which is probably less realistic for longitudinal data. Wow, okay, a lot of movement there. Good. So you include real age, like the actual age at each visit or measurement, and then time in study. And the coefficient of time is then going to be an estimate of progression that's not due to aging. Yep, Satterthwaite and Kenwood-Roger. And those methods you can do in both SAS and R. Well, at least, I don't know if Kenwood-Rogers is in R. Maybe it is. but Satterthwaite for sure is in both. The R functions don't seem to have the containment and between within, which are actually defaults in SAS. But these two are the most conservative, lead to the most conservative test results. Laurel. Okay, so we've had a new leader, like a lot of new leaders coming up. So we have 18, about seven questions left. Good, kriging. So that's the method that we talked about for spatial analysis. And it really is closely tied to linear mixed models and just obtaining best linearly unbiased predictors that you would do in any situation. But we can apply it to, spatial context if we look at data collected, like over different locations, and use the data that we have to interpolate what estimates would be around it. So it's kind of, I like how it's nicely tied into methods that we've already discussed in the class. All right. All right, good job. Markov chain Monte Carlo is that method, and you guys are very familiar with it. Gary gave a lecture on that one day. This is my opinion. Hopefully you would know it by now. What? What? You saw SAS probably first and know that I use it a lot, right? But I was one of my soapboxes was you don't just single out one software. I thought I talked about that.
It was too quick. We couldn't think.
Ah, you're in a hurry to get a quick answer, huh? Okay.
I think it was the if the cost is no issue part.
Ah, okay. Yeah, so what I meant by that was like if you didn't have to buy it, yeah, if cost is, I can see how you could say SAS then, yeah. But I do want to say, I mean, this is kind of important. Like, I know people that are like, I'm an R person. I'm not a SAS person. I'm never going to use SAS. Or I'm a SAS person. I'm never going to use R. You're really shortchanging yourself when you do that. Or even other software, because each software has its strengths. I use R. I do use SAS the most. It's true, but I use R quite a bit, and I'm using it more and more. And R can do things that SAS can't do, and SAS can do things that R can't do. So, and my employer buys SAS for me. If I was on my own, I might not use it. I might not buy SAS, but you want to use things for their strengths and not pigeonhole yourself. You'll be able to do more things in your job if you do that. So, Chloe, were you the one that said both? See, she gets rewarded for that. Let's see if you get this one. I'm not sure if I mentioned this or not. Huh, maybe, apparently I didn't. So I served in the Peace Corps in Lesotho in 1991 through 93. My wife was born in the Philippines, so that was kind of one that might throw you off a little bit.
Where is that?
Lesotho is in southern Africa.
Oh, okay.
So it's that country that's completely surrounded by South Africa. It's kind of unique in that sense. It looks like a little island. And that's where I served in the Peace Corps. So many years ago, but it seems like yesterday. Laurel, did you get that right? Okay, good. Pattern mixture modeling is one of the common ways you can try to address not missing at random data. And it's hard because you're trying to guess at something that you don't have information on. But that's one of the methods that we have for that kind of data. All right, so we have 3 questions left. Still time for changes. Good. Yeah, so Kronecker product structure is used for factors that are crossed. Good. So that's good. I'm glad you got that. I mean, that's one of the important things we learn in this class. You know, that the thing that changes the most are the standard errors of fixed effects when you account for correlation. It also, you know, it changes depending on what correlation structure that you choose. And that's why it's important to understand which correlation structure is most appropriate for your data. And that's why we have maybe, 3 or 4 models that we try usually when we do longitudinal data analysis, and we compare some different models. Usually we use the AIC to do that, but what's going to be impacted the most are the standard errors of the fixed effect estimates. The fixed effects estimates themselves may change a little bit, usually not as much. Denominator degrees of freedom could change, but that usually doesn't impact the results that much anyway. And nothing changes. Good that you didn't answer that one. That's not right. The next question is the most important one. So the boba plot is not that I know of. It's not Italian for sure. And I don't think it's an actual plot anyway. My kids turned me on to boba though. The drinks that have boba in it. My daughter's actually making it now. It's pretty good. Spaghetti plot, lasagna plot, the angel hair. I think was that you, Carrie, that came up with that one?
Yeah.
So yeah. So those we've seen, and the boba plot is not a thing that I know of. So let's see what happens here. This is the final tally. The podium. Elise, 3rd place. Good job. 2nd, Jonathan. And Laura wins it. So congratulations to the winners. If you didn't win, don't worry about it. And there'll be some sort of prize that you'll get for this. I'm not sure what it is yet. All right, so good job. I think for most of the answers, the majority were correct. There was maybe one or two exceptions, but it's because you tried to answer too quick maybe or whatever. So kind of a fun review there. And where are we at? 9:35. So we have still a good chunk of time. And what I thought I'd do next was, let me get out the document. Let's see. There's a review document here. So these are on Canvas. So I kind of just had some different things that came to mind to talk about and review. And we'll do that. And then, and I'm hoping that we can have a kind of a discussion type format. There's not necessarily right or wrong answers here. And I'd like to hear what you've learned in the course too. So we did the game. So Samantha, her project, and she's still working on this, but I happened to look at the data, and we kind of both were kind of doing some model fits for it, and I thought, man, this data is really good for this class because it touches on a lot of different issues that we've talked about throughout the course, and so let me bring that up. So Samantha, maybe can you explain the data real quickly?
Yeah, so essentially there were 3 groups. We don't know, like there was some intervention, but we don't know that. They were asked to step on a Bluetooth scale daily. They were all obese or overweight. They wanted to see if they, how they lost weight over time. There was quite a bit of missing data. So I think for this, it looks like we're looking at daily. When I presented, I looked weekly. Yeah.
Okay, so there's three weight loss programs, right? And they're different. They're telling, they're applying different techniques to help the patients or the subjects lose weight, right?
Mm-hmm.
And so this spaghetti plot kind of shows the data, and there's a lot of data there, but you can still kind of get a sense of what's happening over time just by looking at the raw data. And you can see we do have daily measurements, and the time, what I did was I actually put it in terms of years. And the reason why I did that was because we have age as well. I want to have time and study and age in the same units so that we can, when we talked about like including both of those in order to estimate progression that's not due to aging. And so we wanted to get those in the same units. And you can see, would you expect the correlation, the within subject correlation to be high or low with this data? This is for anybody.
Hi.
High, yeah. I mean, you can see a subject, what they are today highly depends on what they were yesterday, at least in the scale that we have, right? They're not going to go from 300 to 150 in one day. It's going to be a matter of, maybe 1 pound at the most, or maybe a couple pounds or something like that. And so you can see a pattern for a subject moving, but the day-to-day changes are not going to be huge. And that's just that's the nature of the time scale that we're dealing with. Samantha mentioned that she's looking at week as her unit. And so what you can do is you can average data within a time frame. You could do that by week, or you could do it by month, right? There's different units you could use for averaging. The way I did it here is I'm actually just using the daily data. And so if we fit an AR1 structure to the repeated measures, I think we'd expect a pretty high correlation value. What else do we notice about the data when we look at it here?
There's a lot of between subject heterogeneity.
Yeah, there's a lot of between subject variability. One thing I don't have is the 3 cohorts. I could have done that, maybe is to distinguish those. I really didn't do that. So we can't say anything about the specific cohorts here. But
I noticed,
go ahead, Elise. Yeah.
I noticed that most people are following like a downward linear trend, but there are some people who actually look like they're going up over time.
Okay.
I will say what I think was also interesting about this data is one of the groups was measured during COVID. And so while some groups may have like access to like the CU Wellness Center during COVID, that likely stopped. And so that could also be like an upward trend that once COVID hit, they were unable to have access to those
Yeah,
things.
and it would be nice to see which group is which for that
Yeah.
reason. Yeah.
I have a quick question. Do you guys have BMI instead of just weight?
No.
Okay.
That would be interesting to look at. Elise mentioned that there's a downward trend. I noticed that it seems like it's most noticeable in the first half, right? It seems like there's a decrease, and then it tends to flatten out, right? So the model that I have, using weight, and these are the predictors that Samantha used in her modeling. Cohort, time and study, subject age, years, race, sex. And then we talked about this, I think, before. If your research aim is to compare the cohorts, then you might want to have the cohort by time variables in your model, and you might not remove them. You know, if that's part of the main aim, then you wouldn't necessarily take them out just because they're not significant. So those might stay in there. But we have time and study, and so the first day would be 0. And if we use real age, we can put both of those in and then estimate the effects of the treatments that's not due to aging effects. So the basic code, let me run to the end first and just show you what I did. And yes, it's SAS. But we have weight, and then we have real age, time. I put in time squared because it looked like there's not just a linear change. So I put in time squared in the model. I have cohort, and then again, you can include the cohort by time terms if that's important to answer your research question. Sex and race. I put in the final model, I have random intercept, random time, and squared term for time. So we'll be able to get subject predicted values that can, adopt that trend that we see, where we saw some subjects, the trend may be linear and some may be quadratic. Well, what's going to happen to subjects that just have a linear trend? Is it going to hurt to have the quadratic term in here for subjects if they just had a linear trend? What's going to happen in the model?
You're probably going to underestimate at some points and then overestimate at other points.
Well, you would if you force them to have a quadratic, right?
Right.
But when we estimate each of these, for each subject, you're going to estimate an intercept, a linear term, and a quadratic, right? But what if they just have a linear trend?
Their subject-specific quadratic just will be non-significant.
Right. That's right. So we're not going to hurt ourselves if we have subjects that just have a linear trend, then that quadratic will probably be estimated to be 0. So it's going to be a deviation from the population average. The population may have a curve to it, but the subject specific, if they don't, then they may have, in terms of a deviation, they may have a quadratic in the opposite direction as a population average, so to cancel it out, right? Or if there's no actual trend in the population, then their deviation would be 0. So we're not going to hurt ourselves by adding a quadratic. If some subjects don't have a quadratic trend, the estimates will balance themselves out so that it'll show the subjects that do actually have a quadratic trend and then some that don't, by either estimating a 0 or counterbalancing the population average effect so that their trend is, linear or whatever it happens to be. But we definitely do see some subjects that have quadratic trends. So that's why we add that term in there. And then I also have the AR1 applied to the errors. Now let me run back to the comparison. Here's 3 different models that I tried. And again, Samantha, she's doing her project. This may not be exactly what she does for her final project, but this is the 3 models that I chose. If we just put in serial correlation, so if we just put in the AR1, there's the estimate of the correlation. The day-to-day correlation is very high. If we just put in random effects, so the random intercept, the random slope for time, and then the quadratic for time, we get this model. And if we add both, we have random effects for subjects, and we have the serial correlation here. We get a model that provides the best AIC, and there's a lot of benefits here because we can estimate, we can predict subject trends, and we're taking care of serial correlation. This kind of relates to the one question we had in the game that we played. If you add in random effects, it's going to change the correlation. Now, which one's right? Which one's the correct one? It's a trick question, right? There's not a right or wrong one. It's just they're different. And the correlation that we're addressing here is different because we have random effects, but there's not a right or wrong correlation. So what we do, we're making a soup, right? When we add in random effects and we add in non-simple R structures, our goal is to get the best V structure, which is a combination of the random effects and the error covariance structure. And so these correlations have different meanings. There's not a right or wrong, although this model does appear to be better, the one that has both random effects and non-simple R in there. But that's important, right? There's not one, there's not a parameter, an underlying parameter that we're trying to estimate. Really, we're trying to come up with a correlation structure for the responses that is the best for our data. And it seems like adding in both random effects and non-simple R gives us a good not only does it give us a good AIC, but it allows us then to also get meaningful predicted values for subjects because we have these random effects in the model. But addressing serial correlation is clearly important here. I mean, this is a pretty extreme case, but looking at the data, there's clearly really high serial correlation, day-to-day correlation. So just adding the random effects into the model, this middle approach, the AIC is quite a bit higher. And so I think it's critical that we account for the serial correlation in the data. Now, what would happen if we move to weekly data or monthly data? Do you think that correlation would still be as high? It's not going to be that high. And that raises a question: what's the best approach? Should we analyze daily data? Should we go to weekly data or monthly data?
Aren't these subjects weighing themselves once a week?
Not necessarily. Like some people did weigh themselves daily. Some people weighed themselves at least once a week. So if we do an average over a week, there's still a lot of data that we're maybe missing.
What are the pros and cons? So what are the pros and cons of, or what do you think's the best approach? Using the daily data, the weekly data, or the monthly data? And so I'll ask before Samantha says anything, I want to see what other people have to say.
I think daily, just to take care of the degrees of freedom as well.
Okay.
But I don't know. I think maybe just the EPIME says weekly because it's more interpretable and like you could communicate it to somebody more clearly than daily.
Okay. Any other thoughts? There's one issue that I thought about for weekly data or monthly data is that if there's missing data, you know, for some subjects, an average might have 7, right? For other subjects, it might be less than that if they're missing certain days. And so those have different meanings, right, in terms of variability. So what would you do if you used weekly data? What would you do to account for that? What's one possible way you could deal with differences in the number of values that you're averaging?
You could weight people with more observations more heavily.
Yeah, exactly. That would be, and Samantha, that's a suggestion for you then. If you're using weekly averages, you could add a weight statement, and that's pretty easy to do, right? Most of these regression type methods have a weight statement, and it allows you to weight the average based on the number of days that were used in that average. And I think that would probably be a good idea. So I think, yeah, Chloe, did you have something you wanted to add?
In that case, would it create an issue if the people who had missing data versus the people who didn't were different from each other?
Yeah, and that raises another issue about how do we deal with missing data? And in particular, like, you know, we've seen some of you had projects where missing data was kind of mixed, like based on the timeline. It wasn't like, you know, you dropped out and then you didn't come back, you know, and so you might have had a missing value kind of randomly across the timeline. But here, I think there was more of a dropout issue. There were subjects, and I don't know if you can really tell from this graph as easily, but it seemed like some subjects at some point they dropped out, right? Is that true, Samantha?
Because it's an ongoing study, they don't have complete data for one of the cohorts. So it's like we only have like half a year of data for them.
And that's different. Yeah. So, but yeah, so maybe it's not as much of an issue here. But your point, Chloe, is an important one, that we would still need to address the potential for missing data. And just by waiting, that's not going to address it. So you're absolutely right. We need to consider missing data and how we would deal with that. So in terms of the answer to this question, should outcomes be averaged? I think you could average to weekly or monthly, depending on, you know, how specific, what kind of specific questions you want to answer. Personally, I sort of like the daily data myself, but I don't think there's anything wrong with using weekly data, and it may be sufficient in order to answer the questions. It may be able to capture the trends that we're really interested in here. But the thing is, you could construct custom tests that will average time points together anyway. So even if you fit a model with daily data, you may be able to do custom tests of interest that are, you know, averaging in certain ways as well. The other thing I wanted to mention is the variance for the intercept. Are those comparable to the variance of the slope for time and the slope for time squared? Those aren't directly comparable. I know there was a few people that had presentations that talked about this a little bit, but you want to be careful. Sometimes you have a variance estimate for the intercept, and then you have, you know, your variance for the slope of time. It may be pretty small in comparison, but really that's kind of apples and oranges, and you can't compare and say one is not that important just based on the magnitude of the value. I would look at the AIC for the model with and without the time to get a better sense of whether that's going to be important in the model or not. Yeah, so that's all I have there. There's, in terms of the predicted values, oh, there's a couple other things, sorry. We just talked about that one. So if I didn't say anything, then the default DDF approach, I think in SAS would be containment, if there's a random statement in the model. If we use R, I don't think containment's an option, right? So we would typically, I think the better options in R are like the Satterthwaite and then Kenward-Roger, if that's possible. If we were to use a more conservative statistical method, then what's going to happen to these these denominator degrees of freedom? Are they going to get bigger or smaller?
Smaller.
Smaller, right? And that would lead to p-values that are bigger or smaller.
Bigger.
Elise is on top of it. Yep, that's right. But the thing is, like, if we have a big data set, you're not going to notice a huge difference, really. And for these numbers, obviously the 15 times 10 to the third, you'll see little difference in the, I'm not sure what the exact values will be, but those will go down. But my guess is the p-values won't change too much because we're dealing with a large data set, essentially. And even 89 is pretty big. You get into issues of differences when you have a really smaller data set. So here again is the data. And if we get the predicted values, this is what we see. And, you know, we've looked at AIC as one way to figure out what model we should use. But I also encourage you to use an approach like this. Did the model create predicted values that make sense? And if I look at the original graph and I'm looking at the top few subjects, you know, there's a quadratic pattern here. They lose weight and then they gain weight back in the second 6 months. Well, you see that reflected in the predicted value for the subject. You get a nice smooth curve for it, right? And again, there are subjects that don't have as much of a pattern. So they're quadratic when you add in everything. Okay, so we're these are, if I can find my pen here. But their quadratic pattern is not that strong. So this, this is what I have above here is these predictive values. So we're adding in the population, you know, the fixed effects based on our beta estimates. And then we're adding in the random effect estimates, which include a random intercept, random slope for time, and a random slope for quadratic time. And that allows us to get, you know, quadratic patterns for subjects that differ from each other. So some subjects don't have a real clear quadratic pattern, and we get such subjects like this one that really don't have a strong quadratic, and then others that do. And that this alludes to the point I was making earlier, in that we're not going to force subjects to have a quadratic trend here, but if they do, then we'll allow them to have that. So here we do have a subject with a strong quadratic trend. So we can see that by adding these random effects, we're capturing the patterns in the data. And you can see that, like Samantha mentioned, we have a cohort that's still being monitored, and so we only have a certain amount of data for them. But I'm looking at the data, I'm looking at the model fit, and I'm seeing something that makes sense. So sometimes I think you can run into a trouble just by focusing on AIC. Well, hopefully that will get you good results, but it's also good to be able to see that my model's producing predictive values that make sense, you know, and it should kind of mimic the data. It probably smoothed out a little bit. The last thing I wanted to mention was, you know, we wanted to add in real age in the model. So we have real age, and we have time, and we have time squared. So the question is, can we, you know, how do we make sure that we're separating out effects of aging in our time effects? Well, you can do that pretty easily and show that this process, even if we have quadratic time, we can separate out effects of aging by including real age. And you can do that mathematically, just like I did before when we just had the case of just the real age and a linear time. Okay, so you can, that's this point.
I have a quick question, Matt.
This point I'm making here. Yeah.
So for your predictive value stuff, it's in the figure on the bottom, wouldn't it be, I think maybe the way that you would want to construct this figure is you would fit the model to some partition of your data and then predict on the partition that you left out and then see if they agree. Because right now you're fitting a model to your data and then predicting on the same data. Right, so
Oh,
you're
validation?
Cross-validation.
Yeah, so you're kind of overfitting to the data that you have. So you don't really know if this is an actually good fitting model.
Yeah, you could do validation. We haven't talked a lot about validation in this class, but it's something that's commonly used. And so you have to figure out if you're going to do validation, which, you know, I would encourage you to do in general, but there's certain things you need to consider. How much data you have. I think we have a lot of data here, so you could do validation. You could fit a model and then see how well it works with an extra set of subjects. You could do that. You could do what we call an external validation, which is where you take your model and you apply it to another data set.
Mm-hmm.
And like I did that for a risk paper that I just published, where we have the COPD gene study. I fit the model to our data, and then I validated it with a completely separate cohort. And then another approach would be to do another type of internal validation where you're not splitting up your sample into a main data fit and then a testing fit. But if you do, you can apply certain statistics like leave one out, cross-validation,
Right.
where you're actually just using the data that you have and not splitting it into two samples, but you're just
Right.
creating
Well, I still
leave
think you
one
need
out
to.
validation statistics, and that you can do even if you fit all the data to one model.
Right, but I still think
So
that
there's different approaches you can use.
I
Yeah,
think
go
with
ahead.
with the leave one out, I think you still have to split your data. So I think with the leave one out, the way that would work is you would still have, so you'd split your data into 3 sets actually. So you'd have a training set, and then you'd have a validation set, and then you'd have one data set that you leave for testing. And then for every iteration of your cross validation, because you're going to leave one out for every iteration, you kind of test your fits on that validation set, and then you tune your parameters of the
Yeah.
model for that validation set. And then finally, after all of your cross validations, after leaving every one of them out, then you test on your testing set, which you've left that has never been seen before by your cross validation.
Yeah, I guess what I mean is that you do leave one out at a time.
Mm-hmm.
Okay,
Yeah.
so it's not the same as splitting your data into a data that you're going to use to create the model and then a data that you're going to use to test the model. It's kind of a different procedure, and you can actually get the cross-validation statistics. You can request them like in SAS and probably in R as well. Even if you'd use your data for the main model fit, you can request these statistics anyway and get them. So it's not as if you split your data into, you know, your main data fit and then your testing fit, and then you have to keep those.
Mm-hmm.
You leave one out at a time, but you run through all of those, and it will do that automatically for you and report those statistics. But yeah, we didn't really talk about validation a lot in this class, and I do it sometimes, and then other times I don't do it. You know, why do you need to do it? Some of the reasons are, you know, to prevent model optimism. Like your data is you're gonna get a model fit for your data that's optimal for that data. But the question is, how well does your model apply in other situations? And that's the question that's answered if you do more validation approaches. So that's a good point to bring up.
So for like this study, I guess I've kind of been under the impression that validation only happens when you're trying to use it as a truly predictive model. So like for this study, if you were just trying to say the effectiveness of the intervention, you wouldn't need to validate. You would just, you would want to overfit to this data. But if you were trying to say, would this intervention work somewhere else, you might want to do validation.
Yeah, that's right. Yeah, if you're
Okay.
going to use it more for prediction, you know, and future cases, then you're right, Carrie. It's more important in that case. Yep.
Okay, thanks.
Mm-hmm. Yeah, good discussion. Any other thoughts about this data or questions or things that, you know, obviously we're going back to, you know, non-normal outcome stuff here, but I think it's a good data set because it touches on a lot of stuff that's important in the class regarding correlation and other things like, you know, splitting up age versus time and study. You know, we didn't really talk a lot about missing data, but if missing data were an issue, what would you do here? What are a few of the things that you would do to try to assess impact of missing data and account for it? Just ignore it and hope no one says anything. Send it in the paper and just see if the reviewers bring it up or not. what's step one? What's like the first thing that you would do to try to understand, like before you even worry about, let's say, pattern mixture modeling or something like that, what's like one of the first things you can do to try to understand the impact of missing data?
You could look at the relationship between some of the covariates and whether your outcome is missing or not.
Okay. So build a model, like the outcome would be whether it's missing or not,
Yeah.
and then look at the impact of the predictors. Yeah, that's one thing you could do.
Could you fit a model with actually, never mind. That doesn't matter.
Okay. Yeah, go ahead, Benjamin.
I could fit a model with missing data, and then try impute for the missing cases, whether we're using the averages, then fit that model, compare the two if there's any meaningful change in AIC.
Okay.
Yeah.
Yeah, that's a good approach. One thing you can do, I don't know if Chloe, this is what you're thinking, but like if you just compare the characteristics, compare the baseline characteristics of people that were completers versus those that weren't. That just gives you an understanding. You know, it doesn't do anything, but it gives you an understanding of, when I said it doesn't do anything, I mean, it doesn't change the model fit, but it gives you an understanding of, you know, is there a difference between people that completed and those that didn't? You know, and then if there is, then you can decide to maybe pursue further, right? But that's the first thing you want to understand is what are type of people are dropping out and what are the type of people that are not dropping out. That's the first thing you want to kind of get a handle on, and then you can kind of move from there. I wanted to go back to just follow up some comments that I made during lectures. And so I'm looking at the lecture log. I don't know if you guys ever look at this or not, but it may not hurt for you to kind of review this. This is on Canvas. And like maybe before the quiz, you can maybe read through it in more detail. But we talked about, I'm just going to go over the last few notes that I put up here, but we talked about the marginal structural models as a way to estimate causal effects or to try to estimate causal effects. And Benjamin actually asked a couple good questions. And during the lecture, I gave some answers and I felt like, well, I don't know if I really answered that all that well. And I went back and watched it and I realized the question that he asked, a couple of questions that he asked were a little different than how I thought about it when we were in class. And it's funny, it's hard to talk and think at the same time. At least I find that to be the case. And so when I went back and listened to it, I realized what he was really asking me. And so I wanted to just talk about this quickly. So the marginal structural model, we apply that when we want to estimate an effect, you know, of a predictor on an outcome. And we're interested in the actual causal effect, not just an association. And we know in regression that we can't assume that effects that we estimate, the beta coefficients, are causal. In order to do that, we need to go through several more hoops. And when we have longitudinal data and situations where there's a relationship between the predictors and the outcome, and then there's also confounder in there, and there's a complex relationship, we may not get the best estimates if we just put in the confounder as a covariate. We may want to apply the marginal structural model. So I think Benjamin asked, you know, we looked at one confounder, which was symptoms. Well, what if there are other confounders? You could apply this method to account for not just symptoms, but you have to think through other possible confounders that could be in there. And also you have to have them measured, right? We could have confounders that are not measured, in which case we may have to just discuss them as limitations. The other main issue is, you know, we talked about this estimate of interest. Can you guys still see the screen here? So we talked about how we want to estimate the expected outcome when a subject is treated minus expected outcome when the subject is not treated. And in the data, we actually only observed one of the two. And also on top of that, it wasn't randomly assigned. So the thing that we're trying to estimate is theoretical. And we do that by, we try to do that by applying the marginal structural model. But how do we interpret this? You know, I talked about you pick out a subject at random, and then as if you apply the treatment and see what the response is. And then you pick out the same subject in the same exact day and same situation and don't apply the treatment, and you look at the difference. And one of those is a counterfactual because you only observed one of them. And again, also, there wasn't the ability to randomly, you know, assign the treatment or not. So the quantity that we're interested in here is a theoretical one that we're trying to estimate. But I think what Benjamin asked was, well, what about the other subjects, right? So the way that we interpret this, there's a couple ways that we can do it. It's the expected response for a randomly selected subject assigned to treatment minus the expected response for the same subject at the same time, not assigned to treatment. It's theoretical since only one can be observed in practice. But we can also interpret it as the average response for subjects in the population when assigned the treatment minus the average response for those subjects when not assigned the treatment. And if you're interested in specific conditions for other variables, then you can condition on those, like a subject of a certain age or race or whatever. You could restrict that in some way if you want to. But this is really in regression models, you can think of, and this is true in general, you can think of expected value in two ways. It's predicted value for a subject, or it's an average for subjects in the population. Okay. I made some other comments also in terms of that specific lecture. You guys can read in more detail. The other thing I wanted to talk about was this came up in the November 30th lecture about the joint model. Why would we need to build a joint model instead of just building a model for one outcome and then building a model for the other outcome? What are the advantages to having two outcomes fit in the same model? And I kind of stumbled through an explanation, which is actually number 3. But I'll start with, I think the most important one is that it allows for joint inference. If you want to make statements that involve two outcomes and you want to do tests that involve these outcomes at the same time, you're not going to be able to do that if you fit them in separate models. Okay, so that's the most obvious reason that there's a benefit. If you want to compare those outcomes in some way to each other, you know, based on some conditions from your predictors, you need to fit a joint model for it. And an example that I have is, that I'll show you here. This data, this is from COPD Gene. And if you're familiar with COPD and the analysis of subjects that have COPD, you're probably familiar with this graph where we look at, on the y-axis, it's FEV1 over FVC. So FEV1 is a measure of lung function, you know, in 1 second. And then FVC is forced vital capacity. That's like the total amount that you can breathe out. And if that value is small, if that ratio is small, that indicates obstruction. And that's one of the key things in COPD that we're trying to look for is what, you know, which subjects are obstructed in their breathing. So the lower the value, the more obstruction. And then FEV1 we have on the x-axis. So we actually, we can break this down though. Let's see if I can use a pen here. What they do is they create these gold groups, and they basically cut it into these quadrants, and they say, okay, this is gold 0, this is gold 1, this is a group that we call prism, and then there's some other groups down here we actually cut it into, this is gold 2, gold 3, and gold 4. Well, if a subject starts at a certain point, let's say they're here, and then over time we see them progress this way. Well, that progression involves two variables. It involves both FEV1 and FEV1 over FVC. So it's important that, you know, when I do a predictive value, when I get a predictive value, I want to base that on one model, right? So that's another reason to consider a joint model for two outcomes, because their movement depends on those together. And we know that they're correlated. You can see based on this plot, these two variables they tend to be correlated with each other. So that's point 2. The last point, which is the one I was trying to describe, I'll get through this and then you guys feel free to answer questions. If we consider outcome 1 and the mean for that, so this would be the mean for outcome 1, this would be the mean for outcome 2. If we fit one model, we can get a confidence interval, right, for that, and maybe that runs here to here. And we get a confidence interval for the second outcome, and that runs here to here. Well, if we're going to make joint inference, then what can we say about those jointly if we fit individual models? Well, we would say that runs from here to here. We basically can say that jointly mu1 and mu2 are in this region, right? If you're going to try to say something about both of those. But the thing is, if we fit a simultaneous model, and we know they're correlated with each other, actually, I'm not going to do that second graph, sorry. I'll go back to this one. We would do a lot better if we fit a joint model, because that would allow us to do a confidence ellipse, and we could do something like this. Because they're correlated, we can get a even more accurate inference for the joint means. So this would be the boxes if we fit models separately. And then this one is if we do a joint model. We can make more accurate inference. Yay, it stayed. Okay, that's all I had to say, and sorry, we're kind of running late. So in terms of, you know, hopefully you guys have just a few extra minutes. I want to talk about the quiz, which we're going to have on Wednesday. I haven't written it yet. Would you guys be interested in writing the quiz? Some are like, huh? And then others like, no.
Interested in not having a quiz. I think a lot of us would too.
We're going to do something because of the fact I took it pretty easy on you guys as far as homework, right? We're gonna do something, but here's my thought: is that you guys each submit a question to me And then I'll take, like, out of the 15 or 16 questions that I get, I'll choose some of them and I'll put them on the quiz. Does that sound interesting? And so, like, if you write a good question, you get the benefit of having your question be on the quiz. Some would not, you know, but the better the question you write, the more, you know, the better chance it would be on there, and you get rewarded by, you know, having your question on there. If we vote and you guys think that that's a good idea, then we'll do it. We'll use the democratic process here and the majority, but you have to tell me now. So you have to vote now, and you can tell me whether you want to do this approach where you submit me a question. You would have to submit it to me by Friday, by the end of Friday, let's say. And I think I want to do the quiz. I know it's tempting to be really popular and say we're not going to do it, but I kind of want to do the quiz, and you'll be done soon enough. So how many would be interested in you submit a question? One, two, three, four, five, six, seven. I think there's enough. Randy has a thumbs up there. Let's try it then. So you give me a question, and you know kind of the style of questions that I ask. I have a practice quiz on, you know, for the final, and you can do it your own way. Maybe don't even worry about trying to do my style. Do the question that you want to ask. It's okay if you know it, right? Ask a question and make it a question that you know. That's fine. Something that you think is important in this class. It doesn't have to be restricted in any way. So you don't have to worry about focusing on material from, you know, after quiz 2. Like, you can use any material from this class, anything that you think is important that you've learned about in this class, and submit it to me by the end of Friday. I think I'll actually put an assignment thing for it. It's not really an assignment. If you don't submit anything, it's okay, but I'll put it on there just to kind of organize everything. Any other questions or thoughts that you guys have?
Is there a rubric for the project paper?
I've developed them in the past. That's a good question. Let me see what I can pull up, Carrie. If you would need to, like how I would grade it, essentially. Is that what you're wondering? Like the things I focus on? I
think my default is always like a traditional brief report. Like, that's just my experience of scientific writing versus like this being more an explanation of the process we went through. So I'm not really sure which you're looking for necessarily.
Okay, that's good. Yeah, I'll get that. I know that's coming up quickly, and probably a lot of people have already developed things, but let me see what I can pull up. You know, the thing I can tell you right now though is the examples that I posted, you know, and generally people are using the standard format. You know, you have the intro, you have the methods, you have results and discussion, which is fine. But if you pick a different format, if you just, you know, have custom sections, that's fine too. So I'm not saying that you need to follow that standard format. But otherwise, let me see what I can pull up, and I'll get that out today as well.
Matt, I have a question about us writing our own like exam questions. Are we allowed to share those questions and our answers with each other?
That's a good question.
And we kind of have the answer beforehand.
I think no. I would say don't talk to each other. I'd prefer you come up with the question, and it's a good question. It's a valid question, but I would prefer you to just do this on your own and submit it. And submit the answer. That's another good point, because I want to know what you think the answer is, and I obviously see if I agree with or if I could add anything to it. But yeah, so do this on your own and submit both the question and the answer to it.
I know this semester it's going to be the quiz itself, but this could be a good way to make a practice final for students in the future too.
Yeah, that's true.
You know what I mean?
This is actually the first time I've done this, so so we'll see. Hopefully that it's a good thing that allows you to kind of help prepare too, because it makes you think about what do you think's important. You know, the question that you come up with might be related to your project because you focus on that, right, or whatever. It could be something totally different though.
Do the
Anything
questions
else?
have to be related to statistics?
Does it have to be related to statistics?
I mean, you ask questions about your favorite
That's
food.
true. Sure, do whatever. Do whatever you want. I'd be curious to see what other questions you come up with. All right, anything else? I can't do office hours right now. I have to jump to another meeting. If anybody was interested in doing office hours though, is anybody, anyone be interested? I could do another time.
I have one quick question. Did you post solutions to the practice quiz or the homework that wasn't due?
Not yet, but I can do that. So the ordinal regression, I'll post those. Yeah, that's
Thank
good.
you.
Anything else? So we'll see most of you next Wednesday. I'm making
Do you have
special
class on
arrangements for
Monday?
some subjects. What's that?
Do you have class on Monday?
No, Carrie's going to take it early. If you have some hard constraint that you can't do it on Wednesday, you can let me know. But
I was
otherwise,
just wondering if we had like a lecture or something on
No,
Monday.
no.
Okay.
Yeah, so you can just pop in Wednesday, 9
Okay.
o'clock. Otherwise, let me know if you need to meet or anything these next few days. I'm available. Thank you for a good semester and God bless you guys. I enjoyed it. It actually turned out pretty well. The remote thing, I was really unsure about it, but it seemed like it turned out okay. I appreciate the feedback in class. You guys really participated well, and I'm always here if you have any questions on any longitudinal related things or homemade pasta or tamales. I can answer questions on those. So
The Kahoot game was good, I thought.
was it?
That was a good way to review.
Good. Hopefully everyone surpassed 12,000 points that my daughter got. If not, it doesn't matter, but it was fun. Yeah, thanks for doing that. And it was my daughter who I give credit to her for giving me the suggestion for it. So, all right, we'll take care and we'll see everyone Wednesday, if not sooner.
Thank you for everything. Bye.
Thank you. Thank you. And I'll talk more to you, Laurel.
Thank you.